Alright, welcome back. So we're going to continue our discussion of three-dimensional functions, or functions that have x and y as the input. And to do this, for this next step, we're going to be talking about partial derivatives. So just like we talk about derivatives for two-dimensional functions, so y equals f of x, where x and y are two variables, we want to be able to talk about rates of change, or derivatives, for three dimensions. So to introduce this, I just want to compare everything back to two dimensions, since that's what we are familiar with. So in two dimensions, we use the derivative dx, the derivative with respect to x, and this gives us the rate of change. So we think of the rate of change as the instantaneous rate of change, so the slope at any given point. And this is with respect to x when we do dx. So the change in the output over the change in the input. So it's like a slope. So this should hopefully be a review from when you've learned calculus, just to kind of bring back some memories about the derivative being the rate of change. So if I have a function here and some x and y axes, the derivative would just be the slopes of the tangent lines. So we could find tangent lines in various places, and the derivative would tell us the slope of those tangent lines. So in three dimensions, we want to do something similar, but it gets a little more complicated because we have two variables as our inputs, and we can't just look along the x or the y axis like we did here. We have three dimensions to think about. So in 3D, we have both x and y as inputs, and so we're going to need both the change in x and the change in y to talk about rates of change. So we need both the change in respect to x and the change with respect to y, so the derivative with respect to x and the derivative with respect to y, to find or talk about rates of change. So the idea here is that we're going to consider the rate of change with respect to x separate from the rate of change with respect to y. So rather than just looking at the whole function and its rate of change, we're just going to go in the x direction or the y direction and talk about its rate of change. So we're going to define this soon, but let me pull up a graph for you just so I can sort of show you what I am talking about here. We're going to go back to one we looked at before. This is sort of the Pringle chip shaped graph, and I just want to talk about some parts of it here. So what we're going to do is we can look along the x direction or the y direction and then talk about the rates of change. So if I look along the x direction, the positive x direction, I'm sort of going up the hill of this shape, of this surface. And so this corresponds on the two-dimensional level curve to going along the positive x-axis. So this is the x direction. And so we could talk about the rate of change going in this direction. And we could do it from any point. So we could pick another point somewhere on here and then look at the change in the x direction, go anywhere we'd like, but we could look along the x-axis and the change in direction in that way. So similarly, we can do this for the y direction. So we can go along the y-axis here and talk about the rate of change in the y direction. So on my graph, that is the y direction, so going straight up along the positive y-axis. And again, we could do this at any point on the surface or on our graph. So we could go looking at the y direction here, looking at the y direction here, etc., or at any of the points I already drew. Okay, so this is basically our plan. So to talk about the rate of change, we're going to look in the x direction along the positive x-axis and talk about what's going on that way. And we'll look in the y direction in the positive y-axis and talk about what's going that way. It's a later topic to talk about derivatives or rate of change in a specific other direction. So for right now, though, we just focus on the x direction and the y direction. And later on in calculus, we'll talk about how to go in the direction of any vector we want. But we're just sticking to the axes, the basics here. So we have some specific notation that we use for this, and I'm going to define it now with the formal definitions of these things. So just like with one-dimensional derivatives, two-dimensional derivatives where like x and y are our variables, we're going to use limits here. And similarly to that, the limits don't matter too much, but it's good to just see it the first time, and then we'll talk about how we do this. So the partial derivatives of a function, and as we're defining this, let's just say this partial derivatives word, it has partial in it, and the idea is that we're just looking at like part of the change or part of the rate of change. So we're looking at like the rate of change in the x direction and the rate of change in the y direction. So that's why it's called partial derivative. So let's say we have a function f of x, y. Then the partial derivatives have this formula. So what we do is we write f sub x, this is the derivative with respect to x of xy. And then if we want to use another type of notation, we use this partial derivative specific notation. It's supposed to be like a curly D. Some people call it a del, but there's another math symbol called that, so it gets kind of confusing. It's just this specific way we write D's when we're talking about partial derivatives. So this is like the partial derivative with respect to x is how I would read this. And this is of the function f of xy. So this is our notation, and this is equal to the limit as h approaches 0 of the change in the x, f of x plus h, with y fixed, minus f of xy, all over h. So this looks really similar to the limit definition of the derivative in x and y, but now that we have x, y, and z, what we're doing is we're just looking at the change going in the x direction, so we add that plus h to the x, and we're keeping the y the same, so we don't look at any difference in the y. And so how this works when we actually do it with math is that the derivative of f with respect to y, with x, so the derivative of f, let me go back. So what I'm trying to say here is that we treat y as a constant. So what this is, what I just wrote, the partial derivative of f with respect to x, this is the derivative of f where y is treated as a constant. So the idea is we don't care about y and what's going on with it, so we're just going to treat it as a constant, and then we keep x as the variable. So I'll show you what this looks like in an example in a moment, but the main thing to think about here is that we're only looking at the change in x, so we look at x as the variable and everything else is constant. Okay, so we have a similar one for the partial derivative with respect to y. We use that same del operator or the script d, so it's the partial derivative with respect to y. And this is going to be equal to a very similar looking limit, except this time it's the y coordinate that has the plus h. So we're looking at the changes in the y, leaving the x alone. So here we take the derivative of the function f, and we treat x as a constant. So we're going to look at just the change in the y, so we treat x as a constant. And this can be a little tricky to do at first just because we're so used to thinking of variables and as like having multiple different values for them. But with some practice, it should be not too bad. Okay, so I want to show you some examples, but really quick before I do that, let me just give you some more notation. So just like with derivatives that we've learned previously. There's lots of different ways to write the same thing. And so we have a similar case with these partial derivatives with x, y, and z. So let me just write down that more notation for you so that we can start practicing it. What we've written here is the formal definitions of these things, and we'll get into how we use them in a moment, but again, I want to just show you some other ways we write these things. Okay, so if we have a function, I'm going to call it z is equal to f of x, y, then we can use any of the following notations. Okay, so we're going to look at the partial derivative with respect to x, and this we can write as just f sub x. So we can just put that x in the subscript there to indicate that we're taking the derivative with respect to x. Or we can use the partial f partial x, the derivative of f with respect to x. Or we can use the partial derivative with respect to x of f. Or, since we've used z as the variable, we can say it's the partial derivative of z with respect to x. So all of these notations mean the same thing. They're just different, like looking, and they have different things going on, but we can use all of them interchangeably. So same with the derivative with respect to y. We can just do f sub y, the derivative of f with respect to y, the derivative, oops, I wrote an x there even though I said y. We can do the derivative with respect to y of f of xy, or we can do the derivative of z with respect to y. So we don't really have like a specific way we say out loud that partial derivative symbol. If you wanted to be really particular, you'd say the partial derivative with respect to y, or the partial z, partial y, or something. You'd use that word partial in there probably. But you can just say dz, dy, and it's implied by what's going on here that it's a partial derivative since we use that scripty looking d. And I just want to highlight that these are related to single variable equivalents. Like x and y's. So this first part here is like an f prime of x. Then this would be an f prime. This is like saying df dx, or the derivative with respect to x of f, or the derivative of y with respect to x. So these would be like the two-dimensional equivalent. And I think just remembering back to what we already know might help you make connections here with the new notations. So just like we had all of these ways to write the same thing in two dimensionals, or we call it single variable since it just has that x as the input, we now have this three-dimensional way to do it. Okay, so to end the video, I just want to go over two brief examples with you. These are functions we've looked at already in different contexts in these videos for this week, so they should look familiar, and we're going to talk about the derivatives now. Okay, so the nice thing here is that everything you've ever learned about derivatives still applies. We just have to be a little careful because we have more than one variable going on. So we're going to compute the partial derivative with respect to x and the partial derivative with respect to y given our function. And we're going to use the function f of x, y is equal to x squared plus y squared. All right. So let's do the partial derivative with respect to x first. And remember, we could write this as the partial derivative of f with respect to x. And so to do this, we're taking the partial derivative of x squared plus y squared. So I'm just practicing using some of those notations here to get you used to it. All right. So because we're looking at just the change in the x direction, we're going to treat y as a constant. So we're not looking at how y changes, so we don't really care if it's a variable. We just want it to be like a constant. So I'm going to label that y squared, anything with a y, as a constant. I guess any of the y's, right? Not anything with a y, but any of the y's. And then this x squared is our term that has the variable in it. Okay, and so just to really emphasize that, just remember that x is the only variable here. And so we're pretending for the moment that y is a constant. So what we do is we evaluate the derivative. We do the derivative of x squared. X is the variable, so the 2 comes in front, and we have 2 times x. That's power rule. Then the derivative of a constant is just 0. So the derivative of y squared here, when the partial derivative with respect to x, is 0. So the 2x comes from the x squared, and the 0 comes from the y squared, since that y squared is just a constant, and the derivative of a constant is 0. So the partial derivative with respect to x is just 2x. That tells us the change in the function as we go along the positive x-axis, so in the x direction. Okay, let's repeat this process for the partial derivative with respect to y. So again, I'm just going to practice with my notations here. So now we are considering x to be constant and y to be the variable. So I'm going to just label those x's as my constants. And then my y squared is the variable that I'm considering. So as I'm doing this, I'm thinking, okay, yeah, that y squared, I need that derivative, but I don't need the derivative of the x squared. So when we go to do this, the derivative of x squared is just going to be 0, since in this case it's a constant. And then the derivative of the y squared is 2y, since that is the variable we're looking at, is those y's. Okay, and so here, the partial derivative with respect to y is just 2y of x squared plus y squared. And remember, that tells us the change in the function in the y direction. We'll return to these examples when we talk about how to interpret these things graphically, but for now we're just computing them. Okay, let's wrap up with one more example. This is also a function we've already seen. So we're going to compute the partial derivatives. Let's do the derivative here of z with respect to x. So I'll give you a z. And we'll do the partial derivative with respect to y. And here we're going to do z is equal to negative 2x minus y plus 3. Okay. So the derivative of z with respect to x, we're going to be just looking at x as the variable, and we have negative 2x minus y plus 3. So if x is the variable here, this negative 2x is something we're going to need to think about as having a variable in it. But everything else, the minus y and the plus 3, those we can consider both as constants, since they don't have any x values to do with them, so these are our constants left over. So when we do this, we take the derivative of negative 2x, that's negative 2, and then we have the derivative of a constant, that's 0 and 0. So the derivative of negative y here is negative 0, or just 0, I guess, doesn't really matter. And same for the 3, the derivative of 3 is 0. So we say that the derivative with respect to x is negative 2 of this function. So this tells me that going in the x direction, the change is negative 2. So it's constant change going in the x direction. Okay, let's do the similar thing for the change in y. Okay, I've written out what we are working with. And I'm going to label my variable again. So this minus y, this is my variable. This is what I'm going to have to worry about. But the leftovers don't have any y's in them, and so they're just considered constants. So that negative 2x is a constant, and that plus 3 is a constant. Okay, so when we go to take this derivative, I'm doing the derivative of negative 2x, which here we are treating as a constant, so it's just 0. Then I have the derivative of negative y. That is the variable, so the derivative of negative y is negative 1. And then the derivative of a constant is 0. So putting it all together, I have that my derivative with respect to y is negative 1 of my function. So this means as we go in the positive y direction, it has a constant rate of change of -1. Okay, those are our introductions into how we do partial derivatives. So just remember, everything you've learned about derivatives before still applies. You just now need to consider only one variable at a time when the equation has multiple variables in it. We will talk a little bit about how to interpret these things graphically, and then do some more complicated examples in the next 2 videos. Thanks so much for watching, and I will talk to you in the next one.